All right, let's talk about a force that is literally all around us. It holds our world together, but every now and then it gives us a little jolt just to remind us it's there. It's incredibly powerful, it's totally fundamental, and it all boils down to one simple thing: electric charge. We've all been there, right? You're just walking along, you reach for a doorknob, maybe you touch your car door, and zap! You get that tiny spark, that little shock. It's so common, we usually just shake it off. But what you're feeling in that moment is a direct encounter with the very force we're going to break down today. And hey, it's not just doorknobs. It's that crackling sound you hear when you pull off a sweater in a dark room. And on a, slightly more epic scale, it's the raw power of a lightning bolt tearing across the sky. These aren't all different, weird events. They're all the exact same phenomenon, just on different scales. Static electricity discharging. So how do we get from a crackling sweater to the fundamental laws that actually govern atoms? Well, we're going to uncover the two faces of charge, basically by following in the footsteps of the first scientists who started playing around with this stuff using some surprisingly simple experiments. This story actually starts way back in ancient Greece, when Thales of Miletus first noticed that if you rubbed a piece of amber, it could suddenly pick up little bits of stuff like feathers. But the real action started in the 1700s. You had people rubbing glass rods with silk or plastic rods with fur, and they started seeing a pattern, a kind of electrical duality. And it was none other than Benjamin Franklin who gave them the simple names we still use today: positive and negative. And all those early experiments boiled down to one super simple but absolutely massive rule. Think about it. If you rub two glass rods with silk, they both get what we call a positive charge. And if you bring them near each other, they literally push each other away. But if you take one of those positive rods and bring it near the silk you used, which is now negatively charged, they pull towards each other. It's that simple. Likes repel and opposites attract. And this two-sided nature, this yin and yang of charge, has a name: polarity. But here is the really important part. Most of the stuff in our world, the desk, the air, you, is electrically neutral. It's not that there's no charge. It's that there are vast, equal amounts of positive and negative charges all mixed together, perfectly canceling each other out. Okay, so we've got the basics: attract and repel. But what are the real ground rules that govern how these charges behave? Well, as it turns out, there are three unbreakable laws that every single charge in the entire universe has to follow. First up, additivity. And honestly, this one's pretty intuitive. If you've got a bunch of charges in one place, the total charge is just, well, you add them up. A charge of +2 and a charge of -5 gives you a total of -3. The key difference from something like mass is that charge can be negative, so you have to pay attention to the signs. Second, and this one is a really big deal, charge is conserved. When you rub that glass rod with silk, you aren't creating charge out of nothing, not at all. You are just moving some electrons from the rod over to the silk. The rod is left with a net positive charge, and the silk gets an equal and opposite negative charge. The total charge of the system, rod plus silk, is still 0. Charge is just moved around, never created or destroyed. And number 3 is quantization. Okay, this is where our everyday brains have to do a little work. See, it turns out that electric charge isn't like water flowing from a tap, all smooth and continuous. No, it comes in tiny individual packets. Every bit of charge you can find in the universe is a whole number multiple of one tiny fundamental unit of charge, which we call E. So you can have 1E or 2E or a billion E, but you can never, ever find 1.5 E. It just doesn't exist. Here's a great way to think about it. Imagine a dotted line. If you're standing really far away, it just looks like a solid, continuous line, right? But as you get closer, you see it's actually made of individual, separate dots. Charge is exactly like that. We live in a world with so many trillions of these little charged dots that it all feels continuous, but when you zoom way in, it's all discrete. So, we have these 3 unbreakable rules that tell us how charges behave. But that leaves a huge question hanging in the air. How strong is that force of attraction or repulsion? I mean, how do you even measure a force that you can't see? Well, it's time to meet the man who figured it out. This is Charles Augustin de Coulomb. Back in the 1780s, he built this incredibly delicate device, a torsion balance, specifically to measure, with precision, the force between electric charges. And his incredibly careful experiments led to this famous formula, Coulomb's law. Basically, it says the force gets stronger if the charges are bigger, which makes sense. But here's the really critical part. The force is inversely proportional to the square of the distance. What that means is, if you double the distance between two charges, the force between them doesn't just get cut in half, it drops all the way down to 1/4 of what it was. Distance is a huge deal here. So that brings up the question, how much charge is 1 coulomb? Well, you might want to sit down for this because the answer is mind-boggling. If you could somehow take 1 coulomb of charge and put it a meter away from another coulomb of charge, the force pushing them apart would be 9 billion newtons. To put that in perspective, that's like the weight of almost 1,000 fully loaded space shuttles at launch. It's a completely insane amount of force, which tells you that the little zap from a doorknob is a tiny, tiny, tiny fraction of a single coulomb. But this is where it gets truly wild. How does the electric force compare to gravity, the force we feel constantly? Well, let's look at a single proton and a single electron. The electric force pulling them together is 10 to the power of 39 times stronger than the gravitational force between them. That is a 1 followed by 39 zeros. It's a number so vast our brains literally can't process it. The electric force isn't just a little stronger, it's operating in a completely different reality. It totally crushes gravity at the atomic scale. Okay, so Coulomb's law is perfect for 2 charges. But the real universe is messy, right? What happens when you have 3 charges, or 4, or the billions and billions of charges all interacting inside a single drop of water? How in the world do you figure out the total force on any one of them? And the answer, amazingly, is another beautifully simple rule: the principle of superposition. It basically says that the force between any 2 charges doesn't care if there are other charges around. It's like they're in their own private conversation. So to find the total force on a single charge, you just figure out the force from every other charge individually, and then you add all those separate forces up. So let's just walk through that. You just take it one pair at a time. Pick the one charge you care about. Now calculate the force on it from charge number 2, and just pretend nothing else exists. Done? Great. Now do it again for charge number 3, ignoring all the others. You just keep going down the line. And at the very end, you add all those individual pushes and pulls together to get the final total force. And that's really the big takeaway here. From that little zap from a doorknob, all the way to how a DNA molecule folds itself into the right shape, to the very structure of the atoms that make up our world, it's all governed by these simple ideas: Coulomb's law and the principle of superposition. These 2 rules are the absolute bedrock of how charge builds our universe. And that brings us to one last really fascinating thought. We just established that the electric force is almost unimaginably powerful, making gravity look like a total weakling. So here's the question. Why isn't our world constantly being torn apart by these gigantic forces? Why aren't you, me, and everything around us being violently ripped to shreds? The answer, as we saw, lies in that quiet, perfect, beautiful balance of positive and negative.